Our next scientist is really a set of scientists. JJ Thomson, who tends to get the lion's share of the credit, and also a complementary scientist, Goldstein, who did a very similar experiment that JJ Thomson did, but kind of came up with slightly different results. So why do we talk about JJ Thomson? Well, JJ Thomson was around in the late 1800s and developed a model called the plum pudding model, which is a really weird name, but we'll find out why it's called plum pudding model in just a minute. Now, why we talk about this so much is really that it's the first model that's really based upon any type of experimental evidence. This is really a whole new era for atomic theory, and that we're starting to really dig into the meat of what is an atom based upon real evidence. So in this era, it is very fashionable to be playing with electricity. So in labs, a lot of the times we're hooking electricity up to a whole bunch of different things and kind of just seeing what happens. What you're seeing on the screen right now is no exception to that rule. It's something called the cathode ray tube experiment. And you have a tube that's filled with gas, and then we send an electric current through it. Now, the green thing that you see in the back is what they call a phosphorescent screen. It kind of glows with this beautiful light that's stripping across the stream once the electricity is added into this system. So again, we electrocute it and we see this beautiful glowing light. Not very much so unlike what we would see from a modern day light bulb right now. Now, that alone isn't necessarily what's so exciting about this. It's kind of what happened next. Now, just like any good scientist, we always kind of have a question in our head. I wonder what would happen if, and then we start to play. And through that play, it's amazing how much discovery can actually be made. So one day, someone gets the brilliant idea to hold a magnet up to this tube. And JJ Thomson is the guy who works all of this out. Notice what happened to the light on the inside of the tube. Do you see it bending? It's actually bending toward the magnet. Well, JJ got the brilliant idea, hey, well, why don't I hold a magnet up to a regular old light bulb? Do you see the light bending? Well, I don't either. I mean, you'd have to have some sort of a superpower to make that happen. Absolutely nothing happens when you hold a magnet up to a real light. And yet, magically, inside of this cathode ray tube, the glowing material on the inside is bending. JJ Thomson puts it all together and he says, hey, I don't think that this stuff is actually light. And what's really critical about this is he starts to make some additional very impressive observations. So through holding the magnet up to this light, he gets to see a couple things. The south side of a magnet is often called the negative side of a magnet. You can see it's repelling the light. Flip the magnet around, bring the positive north side of the magnet around, and you can see it's actually attracting the beam. Opposites attract, you know. So since JJ knows that opposites attract, there's one inescapable conclusion. The material on the inside of the light must have a negative charge, and therefore matter must contain some negative energy, some negative bits of some sort. And just because everything kind of has to maintain balance, therefore also matter must contain positive bits to match that. This is actually where Goldstein comes in, and we'll talk about that in just a minute. So if matter must contain both negative and positive bits in some sort of a balance, he needs to kind of sit and think and put this all together into one beautiful model. And this is what he ends up coming up with. He decides that there must be these tiny little negative bits floating around in almost a positive like jelly, where all of these forces are together, intertwined, but also in balance. And he needs to come up with a name for this model. Now, he is English, and there is a very famous English dessert looking like this. It's a little eerie, actually, how the model kind of looks like this dessert, typically served at Christmas. This is called plum pudding. So JJ Thomson actually names the model plum pudding model. Now let's put this in historical perspective, just like we did before. So here is our lovely historical atomic timeline. So we can see the work of Democritus leading to Dalton and now to JJ Thomson. And JJ Thomson's contribution is really that now, instead of just a round, solid, kind of uninteresting sphere, there's some interesting structure happening on the inside of the atom. Notice how Goldstein is actually just before him. So let's take a look at how his experimentation was slightly different. Almost an identical experiment. There's only one special difference. Goldstein actually saw the glowing at the opposite side of where JJ Thomson saw it, where JJ Thomson saw a nice green glowing light between the anode and the cathode. Goldstein sees some glowing at the one end, and comes to an inescapable conclusion that this actually has some positive energy to it. So kind of interesting that he thinks that it's really the complementary ray to what JJ Thomson is seeing and calls it positive instead. So again, back to our lovely historical atomic history timeline with adding in the work of Goldstein and also JJ Thomson. Again, the most important thing to note here is that the atom is actually gaining some structure. JJ Thomson's main contribution is that now we both have a negative and a positive part to matter. Not quite sure how the structure all fits together yet, but it's getting a little bit more robust. And of course, the work of our next scientist will start to give the structure a little bit more shape than what we have now.